Everybody. Again, we are here in another Thursday NanoSpin-off talk. I'm Reyes Mayada, director of the Cátedra Sanca de Nanotecnología, and today have a totally different topic from previous talks. We go to the physicist side, and we have here Íñigo Artundo from VLC Photonics, and for the presentation, José María de Teresa, who is a professor in the Institute of Nanoscience and Materials of Aragon, recently created. We are so happy about that. and he will make an introduction about Íñigo, and also he will lead the questions at the end of the talk. I also have to remind you that this talk will be recorded, and then you can access to the talk in the YouTube channel of the Cátedra Sanca de Nanotecnología. And that's all from my side. So, José María, you can start.
Okay. Thank you, Reyes, for the introduction. And thank you for organizing these very nice talks every Thursday. So today I have the pleasure to introduce Íñigo Artundo. So he studied telecommunications engineering in Pamplona. And then he moved to Brussels, where he studied the doctorate in applied physics. He stayed for 5 years there. And then he moved back to Spain, but not to Pamplona, in this case to Valencia. And there he was hired as postdoc researcher, and also he has an MBA. So he has all the tools to lead a company. And as he has told me before this talk, it's very interesting because he's going to cover all the steps from an idea in the lab to a real company. And he has advanced so much that the company has been sold to a bigger company, in this case, Hitachi High-Tech. So it's very interesting to know all these steps, and I'm sure that you will enjoy. So the company provides services for the development of photonic integrated circuits, and some applications are really very interesting, such as applications in quantum technologies, which is today a very hot topic. And I think he's going to provide a unique vision of this kind of spin-off companies, and I'm very eager to hear you, and the floor is yours. Thank you for being here.
Okay.
Thanks a lot, José María.
So I will stop sharing. Now you can share them.
So I'll share the screen. Can you see my presentation now?
Yeah, we can see that.
Okay. So yeah, first of all, once again, thanks to the Universidad of Zaragoza and the Cátedra Sanca and of course José María for introducing me. It has been a pleasure to accept the invitation to talk here. And actually, I want to emphasize how welcome is this initiative here in Spain, and because I believe it's very important to be doing this kind of transfer of technology from research and universities and research centers to companies, and also let everyone know, researchers and the people in general, that the investment in R&D actually pays off and generates a lot of know-how and wealth from that. So the talk of the presentation, the title of my presentation is Pioneering Development Services of Photonic Integrated Circuits. I know that most of the people following this presentation will already have some background in nanotechnology and maybe in photonics as well. But for those of you who are not very familiar, I'll try to make an introduction first, where I will try to answer many questions, starting with the title of the presentation itself, right? So why do I say that we are pioneers? What kind of development services we do? What is photonics, and what is photonic integrated circuits? And you know, everything around that, like how they are done, when do we do it, and where do we do it, and all these things. So let me start by explaining, well, who we are, right? So VLC Photonics started as a business idea more than a decade ago, from some professors here at the Technical University of Valencia in Spain, working on a European-funded research program on photonic integration technology. And because of that, the company was founded back in 2011 as a spin-off company of the Technical University of Valencia, UPV. Since then, we have our offices and also our laboratories in clean rooms in the technological campus in Valencia. And we are nowadays 17 members, most of us with a large background in photonics, most of us also with a PhD and with engineering know-how in photonic integration, because we have been, most of us, working on the field for many years. And the latest news is that since October last year, the company was acquired by Hitachi High-Tech, and we are part of this larger group since last year. So let me then enjoy this opportunity to explain a little bit more about Hitachi High-Tech as well, because Hitachi High-Tech, as you may imagine, is a Japanese group. Actually belongs to the Hitachi group, which is an even larger group. It's really a really large corporation. I was reading earlier today that it's placed in the 106th position in the Fortune 500 global company list. So it's really, really a large conglomerate. And we come to complement the offering on photonic integration with our engineering services and our know-how. As you can see, Hitachi High-Tech has locations in many different countries and regions, and has plenty of technological capabilities, providing services not only on manufacturing, but also in trading around photonics. Observation, measurement, and analysis is the motto. And there are plenty of IP and patents behind that. They also have a large network of customers and providers and suppliers. And because of that, it's not only able to offer plenty of services and capabilities, technological capabilities, but also to really establish a lot of collaborations between different partners and do the networking and supporting customers really from the idea and the production, the prototyping to really large volume production and in a global scale. So this is who we are, but then I would like to explain also what do we do, right? So we are a one-stop shop for the development of photonic integrated circuits. And by one-stop shop, I mean that we try to support customers in all the ways that they are in need for the development of such kind of circuits, okay? From the very early design of the circuits to the manufacturing, testing, and packaging of these circuits. I'll get into detail that later on. But that's our mission and vision. But for those of you that are not familiar with photonics, let me explain. This is taken from the Wikipedia. There is plenty of information online, but I just want to have a very brief introduction to what photonics is. So photonics, actually, it's similar to electronics. The difference is that in photonics, you work with photons instead of electrons, like in electronics. So, and it's the physical science and all the applications of the light. So generation of light, laser light I'm talking about, detection of light, like with photodetectors or photodiodes, and the manipulation of this light. Because the laser light can be manipulated to modulate the light with data. So you can transmit data at very high speed with optical fibers, as probably many of you are using now if you are connected to the internet with a high-speed fiber link. But also it can be used also for signal processing. So you can actually process electronic signals using photonics in various ways. Nowadays, this is being used for computing as well, but also for switching. You can also use the laser light for range finding. For example, you probably have seen these range finders that you can see, you can measure the distance. The most easy use of photonics is this kind of devices, but actually nowadays this is an extension of this is being used in autonomous driving vehicles. So when you have a car and requires a radar that detects all the obstacles around him, people are starting to look into laser radar, what is known as LiDAR. High power lasers are also used in other industrial applications like cutting or more scientific research like astrophotonics, so measuring distances and chemical compositions of faraway galaxies and stars, but also in more practical applications in medicine, for example, in medical instrumentation for optical coherence tomography, surgery as well, dermatology, cardiology, etc. So there are plenty of applications for photonics, okay? So what is photonic integration technology, or more specifically, the photonic integrated circuits? Well, it's similar to electronic integration, right? I don't know what's, oh yeah, okay. The idea to integrate an optical system is to actually put all the different parts of an optical system into a single part, in this case, a single chip, okay? So depending on the application of photonics, you may have setups, like very complicated setups like the one you can see here, with plenty of components and optical fibers and different devices connected all together. And when this comes from research to the commercial product, these are usually enclosed in these kind of boxes, okay, which are still pretty bulky, connecting all the different components. And over the years, different companies, different production technologies have miniaturized that using micro-optics. But integration is actually taking all those little components, the lasers, the photodetectors, the power splitters, the polarization rotators, and things like that, and integrating all those into a single monolithic chip. And this is equivalent to electronic integration, where you integrate different electronic devices like a resistor, a transistor, a capacitor, etc., into a single chip. So it's exactly the same technology, and it's actually manufactured in the same way, but instead of electronic integration or electronic circuits, this is photonic integration using photons, okay? So this was an idea that was proposed in the late 60s when it was proposed to integrate different optical components into a single substrate, into a single chip. And since then, the technology has been steadily growing and maturing to the level that we are now. So why would you do that? Why would you like to integrate an optical or photonic system into a single chip? Well, there are plenty of advantages. They are the same as in electronic integration, right? So you can reduce the volume and the weight of the system. And in some cases, this is very, very interesting. For example, I'm talking about applications in aerospace or avionics, where the volume and the weight is very critical. Or maybe if you want to have a handheld device, you have a large medical instrumentation and you want to miniaturize to have a handheld device, then it's practical to reduce this. Also, because there are not so many components, you simplify very much the assembly and the packaging of the system. It's only one single chip that you need to assemble and package. And this also gives you better mechanical and thermal stability, because you only need to stabilize one single component, which is the chip. But I think what is most important, and what it has been in electronics, it's also the possibility to scale up the system complexity. So for example, you wouldn't even imagine of assembling an optical system that has, I don't know, 1,000 components, right? It will be too complex and too big and too bulky. But these kind of things you can think of when using photonic integration. And it's exactly what it has happened in the electronics, where you have millions of transistors in a single chip, and that you wouldn't even be able to do that with electronic integration with discrete components, right? And because of that, because this is produced in massive volumes using wafers that are lithographically patterned, then you can allow yourself to scale up the production and, of course, reduce the cost in very large series. And this is exactly like it has happened in electronics. So in photonic integration, we are trying to mimic the things that have been working for the last decades in electronic integration. And what has been working? Well, first of all, the software tools, the electronic design automation tools that are used to design these very complex chips. Also, the fabless manufacturing model. Fabless in the sense that you don't have a fab, you don't have a fabric, you don't have the investment of building or setting up a factory to build up, or a foundry as it is called, to fabricate these chips, because this is extremely expensive and very hard to maintain. You just rely on generic foundries that have generic processes, and then you just send your designs to be manufactured in these large foundries. And then, of course, all the reuse of IP and using standards as much as possible in packaging and test, because this has been proven to work in the last decades for electronic integration, and we are trying to mimic the same model. So this technology has been in the market, let's say around 20 years ago. 20 years ago, the devices that were integrated on a chip were very basic, were passive devices like light couplers or light splitters for the emerging fiber optical networks for telecommunications, like fiber to the home, the initial fiber to the home deployments and things like that. Nowadays, actually, the biggest market is not there. The biggest market is not in telecom, but in datacom. So in all the transceivers or all the devices that connect the different computers or switches in a data center. And this is massive volumes here, hundreds of thousands of devices in very large data centers. And since around 2016 or so, when Intel, this very large American corporation, introduced the first transceivers using silicon photonics, I think that was a big eye opener for many people that the technology was ready for production. And since then, the market has been growing steadily at an amazing range. So where is it applied nowadays, this photonic integration technology or the photonic integrated circuits? So as I said, mostly in communications, as I said, in data center transceivers or telecommunication transceivers. Also, people are also using that for communication between antennas and offices in 5G mobile networks. Also, you can find other applications like tunable filters or OCDMA encoders and things like that. There are many other applications beyond communications. They are also being applied in sensing, where you have, for example, the chip being a sensor or the chip doing, for example, the sensing that is being done at an optical fiber, for example. So I'm talking here about fiber sensors in wings of planes or in oil pipes, for example, to detect gases, gas leaks, vibrations. Is being done also for LiDAR, which is the laser radar for autonomous vehicles, to detect the distances to surrounding objects. Also in medical instrumentation, like optical coherent tomography, as I said. In medical diagnostic, like for example, diagnostic chips, lab-on-a-chip devices to test specific proteins or virus detection as well. There are plenty of efforts now to use photonic circuits for COVID detection. And food analysis as well. As Jose Maria has mentioned, also in quantum technologies, there is plenty of applications here. A lot of people using photonic circuits for cryptography, for quantum key distribution, also for generating random numbers, quantum random number generators that they have applications in banking, in online gambling, in algorithm optimization, and plenty of other applications. Quantum computing as well, very hot topic nowadays. And in general, everything related to signal processing. So there is people exploring how to do artificial intelligence and machine learning optimization using photonic integrated circuits, digital to analog conversion, beamforming, etc. There are plenty of applications for this technology. So why do we offer services? Why do we try to support people developing applications using these circuits? Well, photonic integration is a technology that even if it has been maturing in the last 20 years, it's only in the last 4 or 5 years that is really booming. And there is plenty of people that are exploring that because it's transforming some applications and some markets. But of course, it's a new technology. If you compare it with electronic integration that has been maturing for 4 or 5 decades already. So of course, any development is challenging, is expensive, of course, it takes a lot of time, and eventually there are risks that you need to face. And any decisions you make on how to implement your optical system into a photonic circuit can be very critical. Any mistakes that you may have on the development of such a circuit can be very costly to fix later on. So the only way to mitigate this risk, to try to shorten the time to market and avoid also unnecessary costs, is to get support from experts. And this is the main mission of VLC Photonics. Use all our know-how in photonic integration to support customers to develop their own products based on photonic integration. And we have been doing that for the last 10 years. I say that we are pioneers here because When we started 10 years ago, there was no one providing this kind of services. Nowadays, there are more competition arising, but in terms of experience, we have had a lot of learning experience on the last decades in many different projects, in many different applications on what's the right way of developing a photonic circuit and what are the right choices and the right partners to choose when engaging into product development. So how we do it? How do we do it? Independently of the end application, if it's going to be a chip for telecommunications or for a laser radar or for a medical instrument, the development cycle of a photonic circuit, it's always the same. We start, or the customers start with an optical system concept that of a system that they want to integrate on a chip, okay? And the first step is just doing a consultancy study, engineering study to understand if photonic integration actually is able to support that kind of application. What are the trade-offs? What are the advantages and disadvantages? What are the different material platforms you can choose from? Because in electronics, it's very common to do everything in silicon. In photonics, still there are plenty of material platforms. Silicon is one of them, but there is also 3-5 materials like indium phosphide or gallium arsenide. There are also dielectrics like VLC, silicon nitride. So first of all is to map these functionalities into specific devices and select a material platform or substrate, and also an adequate foundry who will be manufacturing this in the future, okay? And it's not only about the technical aspects of this implementation, also there are techno-economical aspects like, for example, is this technology able to scale up to the volumes that I will need later on when I move into production? Are there any IP restrictions? Are there, for example, any challenges that I need to understand beforehand before jumping into the development itself? So all these things related to that. Then the next step is to design the components that will be the parts or the building blocks of this circuit, okay? So it may be a laser or a splitter or a filter, etc. And once you have all these building blocks or these components designed, then you can place them into your circuit and do the layout or the design of the complete circuit, okay? And then be able to model and simulate that. Once you have your circuit ready, then you need to adapt that for the manufacturing foundry that is going to be processing that design. Each foundry has different design rules, so you need to adapt the design to the specifics of the foundry, every foundry. And once the chips are fabricated, because in that sense, we do not do any manufacturing. We work with different foundries who do the manufacturing for us and for our customers. I'll get into that later. But once we receive the chips or the wafers from the foundry, we do the chip, the die testing or the wafer testing, what we call the characterization, okay? And after that, the last step is the packaging or assembly, because at the end, what you have is just a single chip that is very fragile, it's difficult to take out from the lab. So you need something that is put into an enclosure or a housing that is connected with electrical contacts or electrical connectors and optical fibers. And then you can use that in your end application, okay? So these are the different steps that you need to go through. Let me guide you a little bit more in detail of each of these services, because these are the things that we do here in Valencia in VLC Photonics. In terms of consultancy, as I said, we work very, very tightly with our customers to do the technical analysis of the system they want. So review the requirements, the specifications, explain what are the different technology platforms and architectures. Also do a risk analysis to try to mitigate all possible risks, because when you engage into a new product development, there are many. And also evaluate if there are any compliance requirements. But also, as I said, not only technical aspects, but also the cost estimates. What is the development cost of all these stages? How these costs change when you move into production? For example, if there are associated costs like the control electronics for the photonic chip, the packaging, the assembly, you know, all these things. How does this cost scale up in volume when you produce 10 units, 10 chips, 100 chips, 1,000 chips, a million chips? And also, what are the timings in terms of each development iteration cycle, and what are the different milestones to get into production with multi-project wafers, with dedicated wafers, etc. The main activity that we do at VLC Photonics and the core essence of our business is the design of the components and the circuits, okay? So this means that we have all the required tools to model and simulate and design different components and circuits, okay, based on the standard technologies that the foundries provide or other technologies that may be on development. We work with all the major technologies nowadays. So we are not really specialized on any specific technology platform. We serve customers in every technology platform: silicon, indium phosphide, silicon nitride, silica, etc. We try to use as much as possible the libraries of components and the process design kits, the PDKs that the foundries provide. But we also develop our own libraries for customers. And if customers already know how to design chips, because in some cases this is the case, we can also support their teams to do design support or take care of a specific part of the design ourselves. And also support the foundries themselves also to develop their own libraries of components and PDKs. In terms of manufacturing, as I said, we don't do manufacturing, but we broker or we support customers for the manufacturing of their chips. We are fabless in that sense. We don't have a fab, but we have been doing tape outs, so designs for more than 20 foundries over the years worldwide, because we have been working with foundries all over the world. Here you can see some of the foundries we work with for the different material platforms: silicon and insulator, indium phosphide, silicon nitride. Some of these companies are located in Europe, in the United States, in Asia. Some of them are large research institutes that have manufacturing capabilities, or other are commercial or industrial foundries. So there are plenty of choices depending on the project to choose from, and we always try to support the customers in choosing what, in an independent way, what is the most adequate fab and process for their needs, their project needs. Then characterization and testing. This is very critical because nowadays we have to acknowledge that photonic integration technology is not as mature as electronic integration. Okay, for many foundries, still the components or the building blocks are not fully parameterized. They don't have things like compact models that are very common in electronics. In many cases, also new components need to be developed, and the yield, the fabrication yield, is still low if you compare it with electronics. Of course, then this means that it's still critical to do a lot of characterization and testing, not only when you do prototyping, but also when you move into pilot production and engineering runs. But this is very, very difficult because if you compare it with electronics, the tolerances here are much higher. In order for you to have an idea of how difficult it is, the tolerances when doing a photonic connection, an electronic connection with a wire bond are in the order of, the paths are in the order of 60 to 100 micrometers. A photonic waveguide can be as small as 1 to 4 micrometers. So the tolerances here are much higher, and it's very hard to do that in a very fast and reliable way. Not only that, in many cases you need to combine optical testing, electrical testing, and electrical not only in DC but also in RF, in high frequencies. So that complicates the whole testing process very much. And so in general, all the measurement techniques, trace acquisition time, and data processing is still very challenging in photonics. And it becomes even more challenging when you move to production. You still require circuit functionality testing beyond what the foundries provide with their metrology tools. And you need to simplify very much the test plans, but they still get to the right tests to validate the known good dies, okay? So there are plenty of challenges here, and this is what we have been supporting customers with. We have 2 clean rooms here, as you can see, located at the UPB campus, at UPB Fab as well, where we have different tools for basic visual inspection, which is the first thing that we do when we receive the chips from the fab, where we can also do the optical and electrical probing using bird-eye characterization setups. But we also have wafer probers for doing electrical testing and fully optoelectronic testing as well. And plenty of equipment and components to perform all the required measurements and tests as well, operating from the visible wavelength range from 450 nanometers up to the near infrared. and also some capabilities for test assembly that I will comment now. Recently, we have been moving also to wafer level testing, not only chip level testing, but wafer level testing as well. And this is to support the product development and also fill the gap between foundries and packagers, because you really need to scale up and to accelerate the development from moving from chips to wafers. The amount of dice and measurements that you need to do increases exponentially. So you also need to make sure that you get enough information from the characterization and testing to feedback also your design models as well. So we require also automated ID of known good dies, known good devices, and known tested devices to increase the yield. So we have been in collaboration with a tool vendor, Ficontech, to do an automated optoelectronic wafer prober. So you can see here on the photos that we have a full enclosure tool that is ready for production in a thermally controlled chuck. So where we can fit very small wafers from 3 inches to very large wafers of 12 inches, and actually single dies as well. So we can have the capability to test individual dies, and we can do optical testing from 2 sides, electrical testing from another 2 sides as well, DC and RF. And well, the capability to scale up in volumes if needed as well. We offer pure play services for this, meaning that we don't have our own products. So we just test as a service, not only our designs, but also the designs of others. We can support on the review of the layout towards testing to make sure that the layout is ready for testing, because we have seen also in the past that if you don't take, if you don't pay enough attention to the layout, you may find out after fabrication that the chip that you have designed is really very hard to test, or sometimes even impossible. So to prepare all the test program or the test plan, we are able to do the device and also the circuit level characterization, okay? And we have plenty of investment here in our own tools, in our own equipment. We have been certified, quality certified ISO 9001 since last year as well. So everything is well certified, well calibrated, and all the processes are certified as well. And I think what is most important is not the test capabilities themselves, the instrumentation or the components and the clean rooms, but also the expertise behind that. So you really require a lot of know-how of the technology and the physics behind that to do failure analysis, root cause analysis, which is very common when you do prototyping and pilot production. We also do additional services like wafer acceptance testing definition from the PCMs, wafer maps, parameter extraction to build the compact models for the designs, generation of the measurement database, statistical analysis for the fab tolerances. So in order to study the process stability and the yield trends, okay? And also some more advanced developments like the building, self-test, and adherence to standards and certifications. And then one of the latest things that we have been working on is on test assemblies. To simplify the testing and the characterization, we have been working on different assemblies that simplify the testing itself, okay? So we are able to do the chip bonding, the photonic chip bonding into some PCBs or carriers. For RF operation, we use ceramic carriers as well. We are able to do the optical fiber pigtailing in either individual fibers or fiber arrays, and also the electrical connections by using electrical wire bonds or even flip chip with connectorization as well, okay? And if needed, we can also do the thermal management of the carrier. So the idea to have these prototype assemblies is to simplify very much the characterization and testing, to provide an assembly that can be taken out of the lab and be tested in a system level or in a module, and also try to provide a fast turnaround with stock parts that we have at VLC following layout standards. Of course, we also work with many packaging partners that really have advanced packaging capabilities and can really scale up when it's needed for production. So a little bit of our infrastructure in here, you can see as well the flip chip machine, very accurate one, photonic alignment tool. So that's another tool that we have from Ficontech as well. wire bonders, 2 of them, one manual, one automatic, and plenty of equipment to do electrical and optical testing. We can do RF testing up to 110 gigahertz and optical testing, as I said, from 400 nanometers up to 2 micron. So that's everything that we do at VLC Photonics. As a summary, I would like to explain why people work with us, because we have been working for many years in photonic integration, and we have been growing our team and our capabilities in terms of laboratory and software. But eventually people work with us because, first of all, we try to provide lower cost services. The reason for this is that our customers do not need to build a complete team of photonic integration engineers. They can rely on our team and just use the expertise whenever they need it. And also, they don't need to invest on a lot of software tools because we do that for them, right? We have all the capabilities in terms of modeling and simulation tools, clean room facilities for the testing. So they can save a lot of energy in this respect. Also, we are quite fast because we have been working with this technology for many years. So we have access to all the design manuals of the foundries, the process design kits, the people of the foundries themselves. So we can, we can get to speed very quickly. Not only we avoid signing NDAs with foundries because we all have that already signed. So customers can really start development very quickly and reach market very quickly as well. And also, we believe that we try to lower the risk with customers, because when you are not educated in a new technology, and especially a maturing technology like photonic integration, having with you an expert that can guide you on the choices that you have to make and give you advice on the implementation decisions, I think it's very valuable, and we have seen that over the years. And also not only us, but also all the partners around that. So having the right partners to do product development is very critical. So that, I think, has been the key things of our success as a spin-off company, and in general as a design house or test house providing services for photonic integration over the last years. So I hope you had a good overview of what we do at VLC Photonics and the technology of photonic integration in general. And if you have any questions or comments or ideas, I'm happy to talk.
Okay, thank you, Inigo. So many things that can be done with photonics. So, somebody.
Nice talk. Can you hear me? Yes.
Yes.
Yeah. Okay. Yeah, I have many questions, but maybe first we can see if there are some questions from the audience. Okay, I cannot see any questions, so I can start myself. Yeah, so at some point you mentioned that you had some patents submitted. So how important is patenting in your field?
That's a very good question. So yes, we are. So first of all, we don't have so many patents. It's actually Hitachi High-Tech who has a lot of patents. In our case, it's a bit tricky because patenting photonic circuits or the layout of the photonic circuits is not that common. Usually what you patent is the physics of the components themselves, but not the layout of the circuit itself. And there are some IP protection figures like semiconductor topographies, but this IP figure is not extended all over, globally or in all the countries. So we have been struggling over the years of what would be the right approach to patenting, because in many cases we and also some of our customers prefer to just not disclose that and keep that as an industrial secret, while in other cases where there is some technology that is clearly patentable, then of course generating some IP and get the patent on that gives you some freedom to operate, and also give you some security, for example, in case you are raising investment and things like that. But for us, I think it has been very helpful to be up to date with the scientific literature and state of the art. And this includes also, of course, the patent know-how.
Okay, thank you. Another question is related, if you could give us a summary of all the process from to an industry? How much support did you have from public funding agencies such as the ministry or the regional government or the European Union? And also the next step, your company has been acquired by a bigger company, which is normal for spin-off companies. So all this process, can you summarize a little bit your experience?
Sure. So I think when you are developing technology, there are plenty of support programs that you can get access to. Nationally, there are institutions like CEDETI where they have programs like the NeoTech program. Actually, we were granted with this program many years ago that support the creation of technology-based companies. And especially if you are working in an emerging field, like in our case, photonic integration, we got also a lot of support, not in the beginning, but more in the last years with the European funding. There are plenty of tools here for, especially for SMEs. There are many programs that provide good funding when you are doing research or product development, from research development to innovation as well. And of course, you need to navigate through all the different funding schemes and organizations, and getting also support from some companies that support you on that is also interesting. And now we are starting in 2021 with the new Horizon Europe program in Europe. And there is plenty of funding and research topics to work on. So I believe it's, and there are also initiatives to support research being transferred from universities to companies. So I think there are plenty of support in this respect. We have been beneficiaries of this in the past, and I think it's very encouraging from a research point of view.
And this step of selling the company to a bigger company,
yeah.
So was it a smooth process, or there was many discussions in the company and different views?
First of all, I would like to say that there are different business models when you start up a company, and when you develop a product, usually you need to raise a lot of funding to develop the product, because it takes a lot of time to develop a product, and for 1, 2, 3 years, you might not be generating any revenue. So you need to raise a lot of funding for that. And in many cases, also the investors that you require for developing the product and getting this funding want also to sell the company, because that's the way they exit the investment, right? In our case, it was not like that, because we were not developing a product. We were just offering services from the very beginning. So we were never really in need of raising a lot of funding and thus selling the company, because we had the investors eager to do that. So we were growing organically, and it was a very natural choice when we were approached by Hitachi to support them, because they have actually a very similar business model as we do, offering services also for production and development of optical systems, but they were lacking the expertise on the photonic integration side. So we were very well aligned in terms of business model, in terms of technologies, and it was a natural choice for us. So it was an opportunity that we had, but it was not that we were actively searching for that kind of acquisition.
Okay, thank you. Reyes, I think you have a question.
We have a question from this Inma, I think it's Pilar Pina. So you can ask. No, you are silent. Just put the microphone. Yeah, that's fine.
Thank you, Inigo, for the talk. I just start a bit later, sorry, but just a question about the testing of the final assemblies. That you comment that you also offer a testing of the final prototypes, just to find a common point with the research that we are doing. Imagine that we have a problem. I mean, we are using, for example, a standard spectrophotometers, miniaturized ocean optics equipment, and we have previous preliminary data in the lab, so we have more or less idea how to measure and the optical window that we are interested in. So how we can interact with the company? That means we have preliminary data with a external spectrometer, and we want to miniaturize or integrate the photonics in the chip. So how will be the plan? How can we interact with you?
So no, that's very easy. That's the typical question we get. So usually people have an idea of what they want. So they have an optical system, spectrometer or a data transmission system or a LiDAR system, whatever, no? Quantum system. So they have an idea of the optical system, but they don't have a clue on how to integrate that into a chip, right? So what we do is we first ask for a description of the system itself, like a diagram with the different components of the system and the specifications of every component in the system and the system as a whole, okay? And then based on that, what we do is we try to evaluate if, first of all, if that system can be integrated on a photonic chip, because not every system nowadays, at least with the limitations of the technology, nowadays, not every system can be, optical system can be integrated into a chip. And if it's possible, with what kind of trade-offs or performance limitations, what would be our recommendation in terms of material platform, in terms of foundry, etc. And if only if this is all clear, then we can jump into really a development, doing the design and the fabrication and testing. But the first step to evaluate if an optical system is possible to be integrated on a chip is this kind of evaluation. So the first thing that we would be asking from you is this kind of diagram of the system with the components.
Okay, but imagine that we are a totally different field. We are chemistry, or we are from the chemical engineering department, or from the chemistry department. So we know about the about the fluidics. We know about the oxygen that we have in the blood, and we want to monitorize this, and we have the raw data for the spectrometer, so we can give to you just the parameters that we are working with in the spectrometer, in the standard spectrometer, and we have more or less the idea of the absorbance and so on. So this is enough, or? Yeah,
that can be enough. So eventually what you are doing is just testing some liquid, right, with some microfluidics, and then you have like a flow cytometer or let's say a spectrometer that is able to measure some kind of parameters, right? Optical parameters. Yeah, exactly. So in this case, probably the optical system is pretty simple, right? Because you have a light source and a detector.
Yes.
That's it, right? So there is not much that you can integrate there, because the only things that you need is two functionalities, a laser and a detector. So it's not a really complex circuit, right? But for example, in some cases, what we have seen is that people want to integrate, for example, many light sources and many photodetectors to do, and every light source, for example, using a different wavelength. So you can have different wavelengths of light testing different molecules or different whatever. And this can be integrated on a circuit, because what you can do is to have some kind of a splitter that splits light at different wavelengths or combines light from different lasers into a single channel. So all these kind of things could be done. But sometimes one thing that we face is the difficulty to talk to customers that they are very much specialized in their field, but they don't have so much idea on the optical side of things. Because you really, for example, from the chemistry side, you really speak a different language, right? When we talk with quantum people, they really speak a different language. So sometimes doing this matchmaking between your expertise and our expertise in terms of photonic integration is also important.
Yeah. Yeah.
I can imagine. I have also same idea. I also collaborate with her. We are in the same field, and we are working with Raman sensors for toxic gases. We have a very good result, and that will be desirable that you have a handheld system. Actually, there are systems for that, but they're quite robust, and if you can miniaturize that and to put it that in, for example, in the buildings, and to get an alarm for a toxic gas, it will be great. But I'm imagining, okay, we just need a laser, only one wavelength. I don't need more. I have to put it in between my sensing capability, and then I have to have a CCD detector. I think, okay, it's not that much, but I'm thinking in the portable equipment that I have in my lab, and the portable is so big, and I cannot imagine that you can really integrate that in a small circuit that you can put it in a building.
So there are actually people, I can tell you that we know there are people and we have customers exploring that. integrating Raman spectrometers on a single chip using different technologies. So if you want, we can take it offline and I can give you some ideas on the topic.
Yeah, that would be interesting. Great.
Do that.
Okay, I have another question about the fabrication in foundries. What's your experience with that? Because in microelectronics nowadays there is a big problem with the most advanced nodes because the foundries are located either in Asia or in United States. So we have had a lack of components, for example, in car factories, and production had to stop. So I guess that in your case, you don't need the most advanced nodes. So in that sense, you have also, as you mentioned, some foundries in Europe. So what is in general your experience with that?
Yeah, indeed. So for photonics, you don't need such high resolution like in electronics. So most of the times with all electronic equipment, you can build state-of-the-art photonics. And actually that has been identified by some foundries that were, let's say, they were getting old and they couldn't really amortize on the investment that they had. So they saw in photonics a big opportunity because they could, let's say, reuse the old equipment they had to still build, components and devices. Of course, there are some other foundries that are using very advanced process nodes. I think the most advanced process node for photonics, it's the one that Global Foundries is offering on 45 nanometers node, but that is really exceptional. Most of the people are using with 248 nanometers lithography or 193 and yeah, nodes that are not that advanced.
Okay. Raul?
Yes, I have it's more related with your question and with the previous ones. I missed something that, okay, you are doing the design of the integrated circuit and so on, but how do you choose the right foundry for building this one? What is the parameters that you are considering?
Yeah. That's a complicated question.
For instance, if you are planning, yes, and if you are planning, for instance, you say we need to find the way to have the funding, from Europe, for instance. How you are doing this match in order to go together for?
So it really depends on every project because, for example, if you need the circuit to have a laser on the circuit itself, for sure you cannot use silicon because there are silicon is a material platform that does not allow for active generation of light. So you need to use 3,5 materials like indium phosphide. So, or for example, if you need very low losses and no polarization dependency, for example, this is very typical for quantum applications, you may want to look into silica or silicon dioxide, which is a very low loss platform that has square waveguide cross sections that don't introduce any polarization dependency, which you greatly have in, for example, in silicon photonics. So first of all, depending on the application, you choose the material platform like silicon, silica, silicon nitride, etc. For example, also the wavelength range. If you are working, before we were talking about chemistry, if you are working with biological processes that have some reactions in the visible wavelength range, you cannot use silicon or indium phosphide because these materials are actually absorbing light. They are not transparent at these wavelengths. So you cannot build you could build a photodetector, but only that. So first of all, as I said, it's a material platform. And then once you have chosen the material platform, let's assume it's silicon, for example, then there are many foundries for every material platform with different capabilities. So depending on your needs, in terms of components, in terms of price, in terms of time, in terms of potential volumes of production that you can reach. Some foundries are smaller foundries that are working in research centers, while others are very big foundries that require big volumes for production. So depending on the needs of the project, then we choose one or the other foundry.
Okay.
I have one question related to power consumption. So is power consumption an issue for your devices? Because in microelectronics, it's very important. So how can we compare?
It's always an issue. I don't think it's the limiting factor, but when you are moving into some specific circuits that have many active components, like many lasers, many amplifiers, or things like that, heat dissipation and power consumption, of course, is an issue. And especially in applications like data center transceivers, where power consumption is really key for these applications. While for other applications, well, if the chip consumes a little bit more, it's not that relevant.
Yes.
Okay, thank you. Are there any more questions?
I think there are no more questions. Okay.
Well, I have a general question, but I don't know if to ask it or not. Because you are a telecommunications engineer, I wanted to ask you about quantum telecommunications. So do you foresee a future for that? Because we have heard, basic experiments such as a satellite in China that is sending two entangled photons to two cities separated 1,000 kilometers, and entanglement is conserved. So it seems promising, but we seem to be very far away from real applications. What do you think about it?
No, I don't think we are far away. We are actually very close. So there are deployments of quantum key distribution systems in different countries, in China, in South Korea, and actually in Europe. One of the biggest tests of quantum communications is actually deployed by Telefonica. So, and we are actually partnering with Telefonica in one European project, but they have, it's not in R&D anymore. It's something that is starting to become in production. So definitely there is some opportunities in here. It's not only the hype of the research in this topic. It's becoming a reality, yes.
Okay, thank you.
That's very good.
So I give the floor to Reyes. So from my side, thank you for your this interesting discussion.
Thanks a lot.
Okay, I just want to thank you, Inigo, for the very nice presentation and to show us that it's possible to go even quantum communication. That I never thought that is so close. So thank you all for attending this nice spin-off talk. And I hope that if you couldn't attend, people will attend on the YouTube channel. And that's all from my side. We will stop now.